So here we go. This is a quick review for us with respect to the current project that we're working on. It's the project where we're using registers. So in this project, what we're going to do is learn how to take the flip-flops that we're learning about and begin to build them into more complicated circuits that we can begin to do some things that are a little bit more fun. The fundamental building block is the D flop. So when we speak of the D flop, we're always referring to a 1-bit wide flop. The reset is asynchronous in that as soon as it goes high, Q goes low. But when the reset is low, then on the active edge of the clock, D gets copied to Q. So that is how a D flip-flop works, and it's exactly how a register works. A register is best conceived of as an array of D flip-flops. The reset is common, the clock is common, but the data in goes to each of the respective flip-flops and the data out comes from each of them. So in this case, what we have is an n-bit wide register. So within here, it could be 8, it could be 16. There would be 8 or 16 flops all working in concert to build what we call a register. So once we understand how the D flop operates, we can understand how a D flop based register operates. Then we're going to start to come in and incorporate combinational logic, which are gates, to build the different structures that become the building block for the computer systems we're going to use. So the first is we maintain the structure of a register. The behavior of the register is on every active edge of the clock, the value on D gets copied to Q. So if we want to, we can deal with the behavior of the register by adding logic on the front end. In this case, what we want is what we call a loadable register, which means we want to load a value into the register and have that data held until we want to load a new data in. How we load it is the term load that will be high for 1 clock period. When this is a 1, the mux selects the 1 path, so the data on our data in is then presented to the D of our register. On the next active edge of the clock, that contents gets loaded into our register. Then the load signal goes away. What happens then is that the current contents of the register on Q will be presented back around to the D, so on every successive active edge of the clock, we are just refreshing the contents of our register, or we have a register that we can say is loaded. This is a very common structure. We'll use it again and again. It also sets the precedence how we're going to be building our circuits. We have a register, which as we've stated is just an array of D flip-flops. Then on the data path in, we put logic to give us the behavior that we want. Here is below a register that we can either load or count. So when we want to load a value in, we assert the load signal to a 1 that allows the data coming in to get loaded into the register. When the load signal goes to 0, now what happens is whatever value we've loaded into the register passes through this increment circuit, which just means add 1, and now on the next active edge of the clock, Q plus 1 will be loaded into the register, and so on. So if we loaded a 5, then a 6, 7, 8, so it just counts. And the note here is very important to get a good feel of how these behave. Let's say our register was 8 bits wide. That means if we allowed it to just keep counting, it would count starting at perhaps 0, and it would run up to FF. What that means is all 8 bits are a 1. Since there are only 8 bits in the register, that means on the next clock we're going to roll back over to 0. So with an 8-bit counter working in this type of a structure, the counter would count from 0 to FF to 0 to FF. When we write the Verilog for our registers, we have to know how to write the Verilog for a D flop. This is extremely important. We have the keywords module and in module that delimit the module. We have the word flop. You could call it anything, but in this case it's a flip-flop, so let's call it flop. This is the port list, which shows us the connectivity to the flop. There's the clock, the reset, and the data, and then the Q. The input, clock, reset, D, output, Q. Since we're using a procedural block to make the assignments into our output, we must define the output as a register, reg. So then is our design. Always at the positive edge of the clock or the positive edge of reset. If reset is active, Q gets held to 0, else the value on D gets copied to Q. Please learn how to write this. It will be the building block that we rely on. It'll come back in 301, 360, 460. When we want to take and write a register, notice the similarity to the D flop. The structure is identical. The only thing that is different is now the data path through the register is 8 bits wide. So our input is 8 bits wide, our output is 8 bits wide, and then we must declare a register as our data type, also 8 bits wide. The structure of the register is identical to the D flop, with the exception that now when reset is active, we are assigning 8 bits of 0. Then when we're running, the value on D, all 8 bits, gets loaded into Q. Take a moment and look at the different representation, one of the D flop, one of the register. Notice the similarities and then appreciate the difference. The difference only has to do with the fact that the register has an 8-bit data path. Again, we saw earlier on how to write a loadable flop. The loadable register again is identical. In this case, it's an 8-bit wide register. Therefore, our data path is 8 bits wide, and we require a register 8 bits wide to hold the data. But just like the previous example, there is a load term that's an input to the register on the active edge of the clock and the positive edge of reset. If reset is active, we always load zeros. Now, else if load is active, D gets loaded to Q. What is implied here is that when load is inactive, the value of Q remains the same. Some people like to add else Q gets Q. That's perfectly acceptable, although it is not necessary. For our project now, we want to build a 32-bit wide counter. So this is a 32-bit register that will have the logic on the front to allow you to add 1. But the problem is when we look at the next chart, and it's a little fuzzy, forgive me, but you can see this is the time each of the bits in that 32-bit register will take for it to switch states. 0 being the least significant bit, 31 being the most significant bit. Now keep in mind when you count with 32 bits, you're going to count up to 2 to the 32nd. What that is, that's 4 billion. So this is telling us how long it takes us to count that high. The least significant bits change very fast, so fast that we would not be able to see it. As we move up to the most significant bits, you can see at the end, bit 31 switches almost every 43 seconds. So that means 43 seconds low, 43 seconds high. So it's over a second is the period. So it takes about 1 minute, 10 seconds in order for us to count from 0 to 4 billion minus 1. This is remarkable that you are building a circuit that you're counting up to 4 billion. As you look at the other bits, you can see how the different times change. What we're going to do is we're going to add a multiplexer that will allow us to look at these counts in groups of 8. 0 to 7, 8 to 15, 16 to 23, 24 to 31. The design will look like this. We'll build our counter, which we've already seen the template for previously. The counter will be 32 bits wide. What we have to write is a 4 to 1 mux that has 8 bits wide. This will allow us then, with 2 switches driving our select lines, we can look at the LEDs and see them switching. When we look at the least significant bits, when the select is 0, 0, we'll see that these lights are fairly dim, and it turns out that they're switching so fast that the LEDs don't have enough time to charge. As we slow down by selecting 1, then 2, then 3, you will be clearly able to see these outputs switching according to the delays that are documented here. The test bench is simple. All we need to do is provide a reset and a clock. Then what you could do is switch the select bits. The problem is we're not going to run a simulation to count to 4 billion. So once you've seen your select bits switching 0, 1, 2, 3, good enough. You should, though, when you've selected 0, 0, you should see the least significant count showing up on the LED output. That you can verify in your simulation. Then we're going to put it onto the board. Notice that the board has 8 switches. We will use 2 of these for our select, but more important in this case, there are 8 LEDs that we'll use to display the 8 bits that we are counting. This shows you how we connect in the UCF our LEDs and our switches. Please use the 2 least significant switches, and then we'll see the outputs on the 8 LEDs. And then this is the UCF. I still recommend just copying the master and making the appropriate changes. Make sure that the names that you have in your UCF correspond to the top level module. So hopefully this helps. It's a very quick walkthrough of our project. The project is interesting in that you're doing something where you're counting and you can clearly see a count, and then you'll be able to tell your family and friends, oh, what did I do at school today? I counted to 4 billion. Okay, see you soon.